My name is Hank Kosmata. It's K-O-S-M-A-T-A. I was a chemical engineer student at University of Utah, and in our senior year, at that time, the American Society of Chemical Engineers had what they call a senior problem. They gave to all the chemical engineering students around the country. And by chance, the year I was a senior, it was design a nuclear reactor. I had no idea what a nuclear reactor was, but since it was a 3-hour full quarter problem, and you spent probably 100, 150 hours on it, you, at the end, knew a lot about it. And it was fascinating because it contained a lot of the elements of classical chemical engineering, heat transfer, fluid flow, materials. But then you also found out that in a nuclear reactor, there was a lot of difficulties with materials. Some materials poisoned the reactor, some materials aided it. And so you had a choice of all kinds of materials for the fuel, for the moderator, for the pressure vessel or process tubes or whatever you're going to use. So it was really an intriguing problem. And at the end of it, I said, where can you do this kind of work? And they said, well, it's either Hanford or Oak Ridge. And I was a Westerner, so I chose Hanford. So I came up here in January of '54. And at that time, there were 6 reactors, all alike, like B Reactor. They started with B, in operation, and they were constructing the K Reactors. The K Reactors were almost exactly like B and the other 5, except that it was larger. Where the old reactors had a couple thousand tubes, K Reactor had 3,200 tubes, but and a little longer active zone. So they tried to keep it similar so they could use the same fuel, and so they could use the same physics calculations, and they just wanted more power out of the K reactors. As a tech grad, I started on that reactor actually in the construction. We were actually tubing the reactor, and that was part of what I was doing. But the technical grad program here meant that you rotated every 3 months. And on about my 3rd rotation, I got into a group called Reactor Design Analysis. And they were the people that were actually had done the initial design for the K reactors and were assisting in the actual construction as design assistants. And it was a multidiscipline group. They had physicists, mathematicians, chemical, nuclear, mechanical engineers, electrical engineers. So they were able to look at a problem from all sides and did a lot of the more difficult problems for the other design groups. And so as a part of my assignment, I was working on different assisting the senior people, and there were a lot of them, most of them were either had masters or PhDs. It was a really interesting group. Toward the end of that assignment, my supervisor said, you know, one of these days they're going to ask for another reactor. Why don't you look at what you think it ought to be? And it was just a dream. I mean, this is what I came to do. But now I had all the resources that were available from this whole project. I always think that, you know, because I was a junior man, they probably think, what the heck, you know, we can spare him. But it gave me this wonderful opportunity. So what I did was I spent about an hour, or a year, excuse me, on that project. And I was able to talk to all the people that were working there, either in design or in actual construction, go out in the field and talk to the scientists that were doing experiments in various fields. And what we did was to try to gather the technology that had been developed and from B Reactor on and use it in the design of this next facility. The only restraints on this next facility was that it was going to be a recirculating reactor. The old reactors took water directly out of the river, went through the reactor into a retention basin, and then after a short wait there, went back in the river, which meant that if there was any fuel failure or corrosion products, that went back into the river. And although there was a great dilution factor, you could still measure it, and so the public relations aspect of that was not good. And the feeling was our next reactor should use a recirculating system. Well, once you look at a recirculating system, then you think that maybe you can recover the heat from the reaction. And so that was allowed in this design, that I could consider the possibility of a dual-purpose plant, not only produce plutonium, but also power. The things that we gained from the old reactor with this enormous experience in physics to determine how to use the materials that were now available to us, but using the physics calculations that were proven through the actual design and operation of the old reactors. We had some flexibilities now that weren't available to those guys. For example, in the old reactors, in B Reactor and the first 8, including the K reactors, they were pretty much restricted to natural uranium. They had been starting to do some experience with what they called spike columns. They'd use a little enriched uranium to tend to flatten out the fluxes and to get a better power distribution. But now, for this reactor, in this time frame, we knew a lot more about how we could use enriched uranium rather than just natural uranium. And using enriched uranium allowed us a lot more flexibility in what we could do as far as the materials we use for the cooling pressure tubes, and in the way we designed the ratio of fuel to moderator. It allowed us a lot more flexibility and safety. We could under-moderate the system and bolster the reactivity with enriched uranium. There was much more enriched uranium available now coming from the diffusion plants. And we had a good fix on what that cost, so we could balance the cost of enriched uranium and what we gained from that. And this whole design experience was always looking at how can we reduce the cost of the product as compared to what was coming out of the old reactors. And one of the big gains, of course, was to, if we could produce power and sell power, then we could offset a lot of the cost of the plant. We had the opportunity of looking at different materials. The old reactors were restrained to aluminum, and that meant, and that was fine for them because they only wanted to operate under boiling conditions. They never went over about 180 degrees. We now had some information to tell us what the characteristics of a relatively new material, zirconium, would be. It was a very expensive material, and the Navy had been doing some experiments with it. But it also was very reactor-friendly, had a very low cross-section for capturing neutrons. And so even though it meant a very expensive pressure tube, it meant that it could be used efficiently. And so this reactor looked a lot different than the old reactors, even though it was based on that same technology that was gained from B through the construction and operation of K reactors, using their reactor physics and using the material technology that had been developed here and by other government facilities at that time. We started looking at going way up in pressure. This was going to be a 1,800-pound system. The old reactors operated at 180 pounds. We were going to operate at temperatures like 580 degrees. The old reactors were at 180 degrees. We used, as I say, a uniformly enriched fuel. And instead of going to more pressure tubes like they did in K reactor, we actually went to fewer because of the cost of each tube when you're using a heavy-walled zirconium tube. We went down to 1,000 tubes, but we still were going to generate at a design level of 4,000 and ultimately 4,800 megawatts out of that plant, thermal. But with the temperatures and pressures we were operating at, we were able to generate, in our initial design, 860 megawatts electrical. So our design level was equivalent to the most highly efficient power systems at the time. And after, as I say, a year of really going to different people, gaining their knowledge on heat transfer, on fluid flow, on physics, going to different laboratories like Battelle Labs back in Columbus. It was doing some materials work on zirconium. In our own labs, we would do little experiments on, we would heat up uranium, stick it in water, and see what happens when you rupture it. And that allowed us to focus on how we would design the fuel elements to minimize that, the consequence of a rupture. But it was a lot of this trial and error type of calculation, but all based on the old facts that were gained basically from those pioneers in the B reactor days. After about a year, we concluded that study and wrote it up and essentially said, okay, here's what our next reactor should look like, and we called it the new production reactor, or N Reactor. And we sort of set it on the shelf. A year later, the AEC said, have you guys got anything on the shelf? And we said, matter of fact, we have. And so that's how N Reactor was born. I stayed with that operation through the full design of the reactor and the initial operation, and took it up into this higher, into its 4,800 megawatts to demonstrate its capability. At the time, it went through a lot of political gyrations because there was a lot of political dispute over whether we should build a power reactor at Hanford. There were a lot of different factions that didn't want that to happen. The coal industry, the private power companies. So it became a real fight in Congress as to how that was going to happen. And we remained a little flexible on our side from the design standpoint. We designed a reactor so we could sort of accommodate that. So while they were arguing over whether we could ever add power to it, we initially operated it as a plutonium-only facility, and we called it a convertible reactor. Later, when the political issues were resolved and we were able to add the steam generators or the turbines, then it became the largest power reactor in the world. There was nothing like it for a long, long time. So we really made history here, and it was all based on the technology and the experience of those people that went before us. Fascinating time.
Can you characterize some of the real milestones in the B Reactor program? What, things that transferred directly to your designs later?
One of the most important things, of course, was the physics. The fact that they were.
You refer to B Reactor when you say that.
When B Reactor physics.
Sorry. Yeah. Go ahead, because
The B Reactor physics was quite restrained because they had just natural uranium to work with, and that meant that it was you had to have just the right amount of materials, the right amount of uranium, the right amount of graphite to moderate it, and a very small amount of water in the reactor to cool it, and very thin aluminum tubes. All of that had to be really played very carefully together because you had very little flexibility. I think has been mentioned earlier that from a physics standpoint, they thought they could operate with around 1,600 tubes. They found out later because of fission products, xenon particularly, that they needed more tubes. Unfortunately, the DuPont engineers were conservative enough to add the ability to add tubes, but it was on the margin, the fact that they were just barely able to make that reactor operate. But they learned a lot about, of course, in the actual design and then the operation, they learned an incredible amount about the real physics of an actual operating reactor, way beyond what, of course, they could have done in any of the experimental piles. Then they started experimenting a little bit with spiking the columns, a little bit with some enrichment, and they also flattened it out by the use of poison in certain areas. They learned about the control. In the control of B Reactor, they only had 9 control rods, all coming from one side. They found they needed a lot more control in order to efficiently operate. In N Reactor, we had 84 control rods, 40 coming in one side, 44 on another side. In the old reactors, they used safety rods coming down from the top, with the possibility of boron balls as a backup. In the N Reactor, we went to just the boron balls as a safety system. So the knowledge gained not only by the design of the old reactors, but by the actual operation and the operating experiments that they did, sometimes unintentionally, gained a lot of information that, of course, was available to us in the design of N Reactor.
Could you speak to the
I mean, characterize the feat that was, because this was the first of the reactors, and they were really engineering from theory.
B Reactor.
B Reactor. Yeah.
B Reactor, of course, the only physics experiments they had were from CP1, the Stag field pile, where they had limited availability to really do much changes. I mean, they built that and monitored as they went to find out if they could finally achieve a chain reaction. And that allowed them to at least set the parameters for what they believed would work in B Reactor. And fortunately, they it did work, but as I say, the margin was very slim. They just didn't have the ability that we later had to, for example, to add different kind of materials, particularly in fuel enrichment. So they had to be very, very careful about how the materials they put in there. We had more flexibility, but we gained it from not only what they learned in their first design, but also from what they learned as they operated that reactor and the other 6 just like it, and did various experiments. And they learned more about how the fuel reacts over a period of time and different exposures. They also learned a lot about, very important to us, was that graphite was not all that stable. Under different radiation levels and different temperatures, it would either grow or shrink depending on where you were in the reactor. So for N Reactor, we put in a full moderator cooling system, a cross cooling system that was specifically there just to help control the temperature of the graphite in order to help prevent this growth and shrinkage problem that they had in the old reactors. But because of their experience, we were able to get ahead of that.
What kind of feat is that? I mean, given the complexity of N Reactor and the shoulders you had to stand on, so to speak, starting from scratch like that, in that kind of a pressure cooker, the war room and so forth, that had to be some pretty dynamic physics, wouldn't you say?
Well, and of course it's that great combination of the scientist and the engineer, where the scientist is measuring, gaining an incredible amount of knowledge from what looks like pretty crude experiments. And then the engineer is trying to translate that into something that will actually, and expanding it by 1,000-fold. I mean, the old pile, the experimental pile operated like 250 watts. The first B reactor was going to operate at 250 megawatts. So he had 1,000-fold increase in the level of operation, so that the engineers had to try to make sure that they were extrapolating way beyond what you would normally do, and using the material and the information that they gained from the physicists and the chemists that were now being transferred into aluminum and steel and graphite and a cooling system and a backup system and a control system, and it just boggles my mind. I have nothing but admiration for those people.
How about the speed at which it was accomplished? Is that, I mean, given that you've gone through the design of a new and unique reactor?
Yeah. It's amazing how fast they translated information from the field into design. Particularly if we look at how things are done these days. Back then, they would do an experiment in Chicago, and it'd be translated into a drawing and brought out to these guys in the field almost immediately. We still had a fair amount of that ability when we were designing N Reactor. That is, we could actually go into the lab and ask people to do things, and we would get it right away. But nothing as fast as they accomplished during the construction of B Reactor. I mean, they had this concentrated ability to focus on what they were doing and to quickly get a result. And if they needed something, they got it. And it just amazes you how fast that thing took place, and the construction, how fast that took place.
Sorry.
In terms of some of the safety developments, I was just curious about your take on the negative void coefficient, which caused a reactor to shut off as opposed to accelerate, and how that was misunderstood by the public after Chernobyl.
Well, in Chernobyl, when they lost coolant, they gained reactivity, and of course that's exactly the opposite of what you want to do. In N Reactor, we had the ability to overcome that. I mean, when we had what do you call a void coefficient, when you lose coolant, you lost reactivity. So the safety aspects of it are very significant. And that's why it was very difficult to see N Reactor shut down as a consequence of Chernobyl, because the feeling was, well, it's a graphite moderated reactor, therefore it's just like Chernobyl. But that's just totally not correct. I mean, they had the same materials, but because of the design characteristics of N Reactor, it operated in an entirely different way from the consequences of losing coolant, which is what happened at Chernobyl.
People compare the Chernobyl to the B reactor, so they took the B reactor design. To what extent is that true?
I think they used a fair amount of that kind of design. The one thing the Russians did that we did not do here is they put all their reactors vertical, and so the fuel columns were vertical. One of our test reactors was that way, and we believe that that's probably the information they gained at that time. They essentially jumped onto that technology, because there's a lot of the commonality that was discovered when we learned more about the Russian program, that a lot of information was flowing out of here, unfortunately, and out of Los Alamos as far as the bomb theory. So a part of that, there was a thrust at one time in the design of N Reactor that people were thinking about going vertical. And I specifically remember kind of putting my job on the line, saying no way, because there's so many things we don't know about the consequences of stacking uranium. We were talking about a 35-foot column under the temperature and swelling characteristics, and the loss of coolant accident. And so, although it would have resolved some issues people were looking at, it would have complicated other issues. So it became a very dramatic infight for a while, but we fortunately stayed horizontal.
You mentioned going from Chicago Pile to the B reactor. What about the graphite reactor in Oak Ridge? That was supposed to be a pilot plant.
Yeah, you know, the hope was, and the normal way you would do it was you'd do the graphite stack at Chicago, and then that would lead you to the next step, which was going to be the reactor down at Oak Ridge. But the timing was such that they really they didn't have the opportunity to learn what or to apply what they would have learned at Oak Ridge. I'm not sure they would have learned anything more that they needed at Hanford. And of course, one thing they did do is they decided at Oak Ridge to cool with a gas. And that was one of the original concepts that was going to go at Hanford. But almost at the last minute, they decided that they now believed that they had enough reactivity available to them because of their measurements at Chicago, that they could use water. And the water is a lot easier to use than gas. And that's why the switch. And so the reactor at Oak Ridge, of course, it did not have the same characteristics as the one at Hanford.
We're kind of at our window if we need to get
Well, we
rolling.
can run a couple, we might as well run this one out. We've got about 4 more minutes, 5 more minutes. If you've got anything else you can think of.
Well, I say all my experience was with in reactors was in K in the constructions and in N Reactor during the actual design, construction, and operation. So I really never went into the old reactors. And I had never been in B Reactor until a couple years ago when I joined the B Reactor Museum Association. And it was like a step back in time. It's just so fascinating to go in there and to think of what happened. And I've been out there a lot since because I help guide tours out there, but I just love going out there. Great experience.
Why do you think the American public should know something about this Manhattan Project and the work that was done here at Hanford?
Well, obviously it had an incredible effect on our whole society. Even though it was a weapon that seemed terrible at the time, clearly there's all kinds of evidence that it saved many more lives than it cost. And of course it changed our whole way of life. And all of a sudden we were in a new era, a new age, both for good and bad. The fact that we all now had this race to more weapons maybe kept us from going into a full-scale another World War II, and we see that had this balance of terror. So I think that really it worked. At the same time, it also created this technology that unfortunately our country hasn't used as much as it should have. It's amazing that other countries like France have used our technology and basically power their whole country that way. It's very disturbing to those of us that were in the field in that business to see that what we thought was going to be a great new power source basically became encumbered by what I think was over-design, over-emphasis on safety that we didn't need. I mean, these reactors out here, for example, the N Reactor operated safely through its whole history. The Navy program has an incredible history of safe operation. So we just got stopped in this country by people who don't understand nuclear power and became needlessly frightened of it, and coupled up with people that didn't want that source of power to be developed anyway. And so we crippled ourselves in a period when we could have basically solved the problem that we still face, that is how to cut ourselves away from foreign oil. I mean, the solution is here. We always knew it. Other countries, unfortunately, are doing it, like France and Japan and Germany and others. So it's good of good news, bad news. I mean, we were first, we knew what to do, and yet we allowed ourselves to be stopped.